You can see my slides still. Yeah, great. Yeah, and just like yourselves, you know, at University of Queensland, we also acknowledge country and the traditional owners and their custodians on the lands on which we work and meet, and we want to pay respects to their ancestors and descendants who continue that connection to country. So just moving into the talk. So I just realized I've put a title in here that's slightly different to the one that you advertised, Kate. But yeah, it's obviously the same topic. And this talk is going to be a little bit, shall we say, schizophrenic, because I'm going to talk about the digital twin work that technology that we've been building here, and some of the things that are emerging now from that. But I'll finish on talking about a project that I'm running with the NTGS on Pine Creek, and I'll try with a very long bow to connect those two things. And you know, before I go any further, there's always a massive list of people who are involved in any project, and I just want to highlight that, you know, we've got a list of authors, a very cut down list. Particularly Gemma Mitianis here is my research fellow postdoc working on the Pine Creek area. So everything I show from Pine Creek, Gemma's has been driving that research and work, and she's doing some really good work. And then in addition to myself, we've got Ethan Vellicott from Euclidean and Matt Greenwood from GSQ are really kind of key people in helping develop the digital twin stuff that I'm going to talk about. But there's always a list of other people, and every one of these people on the right here from different organizations could easily be counted as authors. Yeah. Now, moving forward. So some of you probably have heard the term digital twin, but won't really know what that is, except in kind of very vague terms. So more specifically, it's a counterpart of the real world, and it's used for simulation, integration, testing, monitoring, maintenance. And in our case, we're building a twin for the purposes of visualization of data and data discovery. And a key part of digital twins is that you have your physical entity, the world in our case, and then there's a data connection, and then there's the twin itself, the virtual counterpart. And in the geosciences, in exploration particularly, or in any form of kind of field-based geology, those data connections are things like drilling, geophysical and remote sensing surveys, different types of mapping. And a key thing about digital twins is that they are basically ways of absorbing and integrating together massive scales of data. And these things are continually updating. And in our case, you know, that is actually really true. In the department in Queensland, the data connections are basically the drilling data that's coming through on a regular basis from industry, and is being released 5 years from the moment it's received. So that means that there's kind of a continual throughput of data, core scans, logs, exploration lease surveys that are feeding into the Queensland open data portal, or will be. There's also, of course, the work that the survey does itself, and any kind of data that research organizations put together and release publicly. And the reason why we're doing this is because we have a nice problem to have. We've got a nice problem, and that is there's a lot of data out there. And the problem is finding it, putting it all together in a way that makes sense for the problem that you're trying to address, and then, you know, being able to download it and analyze it. So I've just put up here, thrown up 4 different kinds of data portals that exist. There's lots of data portals which industry and researchers and surveys routinely access or generate. You've got the Allscope ones, we've got the GSQ, the Queensland Open Data Portal, we've got things from Geoscience Australia, and of course there's equivalents in the NTGS and South Australia and WA and so on. So there's multiple locations for data. There's global data sets as well that come from NASA and you know, different satellite providers. This data is what we would call continually updating. It's unconstrained and it's heterogeneous in nature. So it, you know, it's not, you know, drill core is effectively a point sample. Aeromagnetics are 2-dimensional to quasi 3-dimensional data sets that spread over large regions. Seismic is 2D, but in the vertical dimension as well. So these are all very different types of data. They have different file formats. They have different distributions. Some of them are you could consider continuous, and some of them are very discrete. We all know that there's a big problem with legacy data. So we have, you know, different file formats for leapfrog projects over time, or for even for, you know, different types of geophysical data over time. And there's not been we haven't done a very good job of standardizing the file formats up until now. And even when you dive into the same sort of file format, let's just take a CSV file, for instance, of geochemistry data. The way that the data is presented, the vocabularies we use, the codes and the dictionaries that we use in those CSVs to describe things like assay information and labs and analytical techniques, they aren't standardized either, not nationally, not in a consistent way. And we're trying to get there, but we're not there yet. So those are the sorts of things that cause problems for consumers of data, and these are the kinds of reasons why what we've tried to achieve is a future where we can actually see all this information in one location. We can see it in its full 3-dimensional glory, how it relates to one another. We can see it at all scales, from microscopic up to state or even national scale, without your computer falling over and breaking. And in order to achieve that, I've been running a project with a group known as Euclidean, who began life as a gaming company, but basically branched out because they realized that their specialization was the ability to project or visualize enormous amounts of data. And the way it works, this diagram here is what we call a software architecture map. And the way it effectively works is you have your real world that is supplying information in lots of different ways, different formats and different styles. That gets absorbed into the cloud. And in the case of Queensland, a lot of that data actually goes into their database repository, which they call Open Data Portal. And from there, the cloud system will pull, using APIs and JSON files, that information out. It then converts it into a file format, which is known as a UDS, unlimited detail file format, .uds. And basically what that is a point cloud. And those point clouds are then stored in this cloud, and they are very effective file formats for visualization of the data. And then one of the smarts behind this system is you go from your cloud and you obviously stream your information to people's PCs or laptops or even tablets in the field. But it's doing it in a very efficient way. So what you actually see on the screen is only what your eye is capable of visualizing at any one time. That means that the system does not need to download to the user all the data that is in the cloud. It only downloads, streams to the user what they are physically looking at that moment in time. So it's a very optimized way of visualizing data. And that means that we can build a true digital twin at the national scale, and it's what I would call seamless. We've been able to show that you can actually, and I'll show you in a minute, you can actually scale information from X-ray tomography scans of drill core. You can look at core photos, and then you can jump right out to look at regional scale seismic or geophysics or other types of data. And I've been able to demonstrate the use of the cloud on a tablet in a drill core yard, drill core shed, connected to the 4G mobile network. So that proves, its utility. It was a bit slower, but it was still able to handle that kind of Wi-Fi constrained environment. Right. So the program of work, this has been funded by the Department of Resources here in Queensland. And in the first year, in 21 to 22, we basically built a proof of concept. And then this last year, we've been working with Esri, who produce ArcGIS, to demonstrate that we can integrate our proof of concept into Esri products. And in Queensland, there's an online tool called GeoResGlobe, which basically is a GIS type tool that Esri manage on behalf of the department, working with their spatial information team. And they serve up through GeoResGlobe mineral lease data, geological maps, any kind of geoscience, minerals geoscience data that they have available in their databases. And we wanted to show that we could actually turn that into a 3D, bring in a 3D environment to that GeoResGlobe. And we've been able to demonstrate that this year, and I'll hopefully show you some of that as well. And then by the end of financial year next year, we aim to have a productions level standalone twin, which will be this digital twin available to the public, where people will be able to go in and look at all the minerals geoscience data for Queensland, or at least some of it for Queensland in its kind of 3D glory. And the aim behind that is that this becomes a data discovery tool. So you can go in and you can see what's there. And then you'll be able to, if you're interested in a particular mine lease or exploration lease or a particular area of the country, and you identify the data sets that are of interest to you, you'll be able to click on those and it'll take you to hyperlinks that will download the primary data from its source. So it'll be a way of not only seeing the information and how it all relates to other information, but also a way of downloading it. The kind of work elements that we've been involved with, kind of major pieces of work that has come into this is, there has been an element of seismic reinterpretation. So we've actually taken a lot of reflection seismic from Queensland and done pure classic geological reinterpretation of that, and then use that seismic to create 3D models. And those 3D models and the seismic interpretations have then been absorbed into the twin. We've had a team of students and research assistants having a go at cleaning some of the legacy data. And that work is really quite nascent. There's a lot more that needs to be done there. But it's in progress. The way of doing it, the way of working, the methodology that we've used is known as an agile development. So that means that for some of this work, particularly this last year with Esri, we had 2-week sprints, so 2 weekly meetings where we would plan out the kind of work that's going to happen for the next 2 weeks, and give the software developers very clear guidance on what they needed to achieve in order to be able to make this tool functional, and what while we were off also, collating the data and guiding people through the intricacies of file formats and so on. And then another piece of work that we want to do is both in-house and out, external facing workshops with industry, showing this data, showing the twin as much as possible, getting feedback, and then eventually getting people to actually beta test the tool for themselves so we can improve its design. All right. And here is a real-time video of the twin in action. So we're zooming in at the moment, and you can see that there's a project tree on the left with various types of data, geophysical, geological, mine site projects, and so on. And I'm just cycling through the regional data, zooming in underneath the topography and showing you the regional seismics that's been reinterpreted that I was mentioning earlier. These coloured lines, they're actually all they're the AEM, the national AEM lines that GA have collected recently. And we're just showing a subset of those in this video. These purple colours are surface geochemistry samples, so stream sediments, rock chips, and soil chemistry samples that have been collected over Queensland, and I'm just turning off various sections of maps that are overlaying those. But you can see they have different colours because you can filter them by assay, and that's a sort of process that's going on by using this little toolbox up here. Now that video is going to keep playing, and I might jump into it every now and then. I'll carry on. What we're doing here is we're just demonstrating that you can jump from one mine project to another. So one of the classic problems with existing proprietary software like Leapfrog or Micromine or Serpac or anything like that is you can build very intricate, detailed models, geological models and resource models of individual projects, but you cannot easily show that data alongside another project or another mine site or with the regional information as well, just because the projects get so large the computers can't physically handle the processing, the computational power of having all that information in one location. But because this is cloud-based and has that optimization approach, you can jump from project to project. So we've just jumped from Walford Creek to Mount Isa, and there's information here. This is a 3D model from Mount Isa, and all this data was supplied by the mine, but you can go in and turn off individual 3D surfaces. You can see there's a whole bunch of cross sections that were scanned from the literature that go through the Mount Isa ore body. These pink surfaces here, those are actually the copper ore shell for the ore body. And so I'm just siphoning through as a demonstration the types of data that can be put in here. And in a minute, we're actually going to jump to individual outcrop scan that's at the surface above the Mount Isa mine. This is the Urquhart Shale. This is a scan that was taken from LiDAR attached to a little tablet that Rick Valenta collected. He was literally walking along the pavement, scanned the surface, and you can see in 3D there the Urquhart Shale relative to the other geology and geoscience information that's present in Mount Isa. And so you can collect and show off data at all those different scales and then embed them and begin to compare them, which is quite powerful. Now, this is Ernest Henry, and I'm just showing a variety of different maps and geophysical surveys that are present there. But what we're going to do is we're going to zoom in underneath the geology map that's projected at surface and see that the copper shell for the Ernest Henry mine relative to, I can't remember what those sections are, but it doesn't really matter. Gives you the idea. And we're just turning on there the magnetotelluric data that exists for this part of the world and some of the seismic. So if I zoom out here, there's the AEM, and you can just see in the background the MT data. And in this particular visualization, it looks a little bit sparse, but actually it's a lot denser than that. But one of the points that we're trying to make here is you can see this finger of conductivity that's coming up through the earth. And right above that, at the top of that finger, is where the Ernest Henry copper mine was. And then we're zooming back into that Ernest Henry copper mine, into drill core. And you can see here the drill core photos. And individually, this here is a 3D X-ray tomography scan of drill core from this core. And just in the background is the logging. So we've gone from regional scale data down to micron scale information. And you can see that the computer hasn't really struggled. It's been fairly seamless moving in and out. There hasn't been any lag. Now, one of the last things I just wanted to mention, and you can see this text that's flashing on the right, we've just began to bring in ESG data. So environmental data sets, social community data, and governance data. And we did this as a bit of an experiment, but it's actually proving something that's really exciting and useful to the industry. The junior mining sector and organizations like AMEC are really very keen on that, because for the first time, there is the potential to have alongside your geoscience information a lot of the ancillary data that's really important for responsible behavior, for making good decisions in the field, for exploration lease management, for stakeholder engagement, and for permitting. So that kind of information is going to be really, really useful for doing true prospectivity. I mean, we like to do area selection and district selection in the industry on the basis of the geological information that's present, and our ideas that we might be generating around target selection. But sometimes projects may have the best looking, most prospective geoscience information that really leads us to believe that it's worth exploring, but we realize that down the track that project just often falls over due to community or environmental issues that weren't necessarily appreciated in the beginning. And the potential here is we could have a tool that enables you to do that kind of assessment very early on. Right, moving on. This is just a demonstration of the integration with GeoRes Globe, and hopefully that video is playing. So I mentioned that we worked this year with Esri, and we just wanted to demonstrate that you could make a 3D GIS environment. You could add in a 2D GIS environment. You could add in a 3D by integrating with our tool. You could add in 3D elements, and that's what we're showing here now. So the video is just playing through again in real time, and this is a classic way of interacting with GeoRes Globe. They have these layers which you turn on and off, and we're showing there the surface geochemistry and the AEM data against the background of the statewide geology. But as we zoom in, we've turned on this little tab down here known as Euclidean, and hey presto, you can go beneath the 2D GIS surface and you can begin to see that 3D data. And what's nice about this is it's showing the 3D data, the seismic in this case, in that really high resolution fidelity. So you can see all the colors and all the textures. Whereas classically in the past, this sort of environment really struggled to do that in a way that was quick and seamless and maintained the resolution of 3D information. So that's been a very powerful demonstration that we can work, that what we've built is compatible with existing tools that service providers and industry and surveys already use. So we're not trying to build a tool that will replace those things. We're trying to build a tool that can work alongside them and but bring that 3D data discovery capability that isn't really out there yet at all scales. So in terms of digital twin, what are the next steps? Well, I've mentioned the ESG elements. That proof of concept there is going to be taken forward. So we really need to do a piece of work now where we work with groups like AMEC and environmental agencies and the junior mid-tier mining sector and ask, well, what are the key data sets that should be shown, and how do you visualize them? What colors do you need? What is the best way of presenting this information? But if we can crack that and even bring in things like critical metal information, then that will make the tool very versatile. Then, of course, this kind of environment is really well developed for things like XR capabilities. In other words, things like augmented reality or virtual reality goggles, immersive rooms. There's kind of nice emerging technology component to it where you can really sort of get yourself and a whole bunch of collaborators into the same room or into the same environment all at once, and really sort of experience the data in all around you. Within Queensland, I mentioned that we want this to be a production level tool by mid next year. But the data that tool will be feeding on won't come just from Queensland. It may also pull on information from GA and Ozscope and CSIRO, anything that's basically in the public domain. There's a piece of work here where there's a need to use a sort of a technique to help with the coal seam gas industry and landowner stakeholders. They want to know where people are drilling and where those boreholes are going underneath their land. And then there's an element here where we can actually further develop this tool for public-private partnerships and national scalability. So we really are very interested in bringing in new partners, extending this work beyond the borders of Queensland into Northern Territory or New South Wales, working with industry as well as surveys and so on. And then just as a plug, one of the other things I'm doing a lot of work on, as you can see this image down here, is with UAVs, drones. And the technology that underpins this digital twin can also be used to do real-time 3D visualization of data. So while your drone is flying and collecting information, we can be visualizing it potentially in a twin type environment or on your laptop or computer while it's flying. And that becomes really important, particularly if you're doing things like geophysical surveys, or you're flying over very large areas and you want to know whether you have missed bits. You want to use that real-time capability in terms of QA/QC. There's also applications there actually for industry and for things like blast hole design and implementation, and real-time resource updating and modeling. So I mentioned at the start of the talk that I'd then finish with a bit of Pine Creek. And the reason why I want to talk about Pine Creek is, we have a project going with the Northern Territory Geological Survey on this part of the world, and it's a focus now for the year ahead, the next few years ahead. And B, this particular region and domain is going to be it's just a classic example of the sort of place where there's a lot of data available, and we really could bring that into the twin environment and use it for the benefit of industry. So just a brief introduction. I'm pretty sure that everyone online here already knows, but for anyone who's watching this video afterwards, through the links that go out, the Pine Creek Orogen is obviously at the top end of Australia. Its location is shown here in the top end of Northern Territory, and it's the geology that's sort of been mapped and identified kind of at or near surface is shown in the brown here. It's a Paleoproterozoic sedimentary and volcanic sequence. It's unconformably overlying Neo-Archean basement. And it's often it's intruded in lots of places by mafic rocks and granites, again from the Paleoproterozoic. Now, one of the interesting things about this part of the world is certainly the central domain. It's broken into 3 domains, but the central domain has an external reputation as being a gold-rich province, and it's, you know, people like Richard Goldfarb have published on that and have used it in many of their paper reviews as a type example. But in reality, this orogen has a large range of commodities. We're all probably fairly familiar with uranium deposits that exist over to the east, famously represented by Jabiru. But there's also, you know, there's lead, zinc, silver, there's platinum group elements, there's copper, cobalt, nickel, there's iron, tin, tungsten, tantalum, and phosphate resources within the orogen. And some of those polymetallic elements are present within the central domain. And this is a piece, you know, the renewed focus on this is being generated by our current need to go through the energy transition. So we really need a lot of these alternative metals for the renewable energy, the infrastructure that we have to build, and to achieve net zero. So that demand is what's driving a renewed interest in places, parts of the world like Pine Creek. And the NTGS are doing a great job of reviewing the data that they have for the region already. And Gemma Mityanis and myself have been engaged to work with them to sort of review the central part of the orogen. And Gemma and I are inspecting the maps, building cross sections, and constructing a 3D model of the orogen, both to provide a resource to the industry, but also to really help us identify where the gaps are. What do we know about stratigraphy? What looks a bit dodgy? What needs updating? What new kind of geophysical data should be collected and remote sensing data should be collected over that area to really help stimulate and support the exploration industry in that part of the world. So there's 3 domains I mentioned, and they are just shown kind of vaguely on this map. You've got the central domain here, which is going to be the area of focus of the rest of this talk. You've got the Litchfield province off to the west, and the Nimbawa domain to the east. And there are some question marks over whether those domains really all should be classified together as part of the Pine Creek Orogen, but that's a piece of work that has to be done, and we'll leave aside for another day. Broadly, though, the central domain is this green schist and low to mid green schist fast schist domain, apart from where you're in contact orals around granites, where you can obviously get you can get amphibolite grades. And the kind of sequence, the broad scale sequence of events that have occurred here is you've had 2 unconformable sequences of sedimentation in the Paleoproterozoic. There's late deformation, metamorphism, and intrusions of I-type granites, most famously known as the Cullen Supersuite, which is all these granites here. And the kind of gold that has been talked about and discussed in this area has been classified as syn intrusion gold, intrusion-related gold, or kind of more classical orogenic lode-style gold in kind of sheeted type veins. And there's been a bit of a debate over whether there's one model applies or both models, or are they in conflict? Are the 2 gold mineralizing events, or is it just one and we're getting confused by the presence of granites, and those sorts of questions. And we're not, Gemma and I are interested in those sorts of research questions, but they're not the main focus of what we're doing here. The area of focus is in the central domain, and one of the intriguing things about it is a lot of the gold mineralization that's known is found around the margins of the Cullen Supersuite granites. but it's also on the margin of this central trough, which was identified from gravity. Now, the key authors who've worked on this area are kind of listed here. And there's been a lot of work that's been done in the Pine Creek Orogen, but it's quite notable that it's beginning to get a bit dated now. And the last work was really done 10 to 20 plus years ago. And techniques have moved forward, understanding has moved forward. And so there's really a need to refresh. This slide here is very busy. I'm not going to go into it in detail, but it just outlines a project that Gemma and I are engaged with, which and the workflow that we're going through. So, you know, the classic desktop review, literature and data. There's an existing 3D model that we are pulling apart and inspecting. We've identified gaps and inconsistencies, particularly in the maps at different scales. We're looking at drill core information as well where we can, and data from industry where it's been supplied. And then we're going through steps of, you know, validating basement interpretations and structural interpretations, working on a reinterpretation of the map in the area, building cross sections, using forward modeling to validate those sections, so that you end up having a geometrically and physically permissible model. And then from there, we will construct a classic leapfrog 3D model. But we can, at this point, you know, with all these steps, that we get back to the digital twin idea, because there's an awful lot of information that's available, a lot of information that's generated. There will be different stages of interpretation, and all that could be consumed into a digital twin. And even the very same digital twin that the Queensland data is in, so that you'll be able to see the Pine Creek data in relationship to, say, the Queensland data. Now, the ambition behind this project is to go through this so we can really identify gaps and make recommendations for future programs of work to the survey, but also to provide a preliminary 3D model of the central Pine Creek Orogen area, which will be provided to exploration companies and hopefully help them in their efforts in the domain. Here's a map that Gemma's put together for Pine Creek Orogen, based on you know, existing interpretations. And this map will change slightly. We've found there's various inconsistencies, which we're not going to go into in gory detail today, but we've noticed things like faults, different scales of map. We've noticed things like faults in different locations, geological boundaries shifting by up to 200 meters. The seamless geology map that you're seeing here is not always consistent with the geophysics, and it's not always consistent with the outcrop mapping. So there is definitely a program of work that's required of QA/QC to update things. But in gross scale, the features that you see won't change dramatically. And I just want to point out that you know, you've got a sequence here of the woodcutter supergroup, the Cosmo supergroup with different formations, which are shown in the brown and the cream colors. Intruding into that, you have these dolerites. But this woodcutter supergroup down here, particularly with the Mount Partridge, is becoming an area of interest for us, and I'll touch on that in a minute. And then up here on the top of the sequence, we've got the Cullen Supersuite, which are all these granites shown in pink, and they are the ones that which the gold mineralization in the area is found to be spatially proximal to. So there's a lot. I mentioned there's a lot of data in this area, and here's an image of the gravity. You can see that the gravity picks out very nicely the granitic bodies that are in the area. And one of the things that also comes out, the individual green triangles here are the gravity stations. So you can see that there's actually some fairly large gaps There's a lot of data that's been collected around the margins of some of the granites, but further outboard, your gravity stations are only 10 kilometers apart. And that probably means that some of this data is not reliable in the sense that we don't really know that there's no gravity stations in here, for instance, and you have a very sharp boundary of the gravity along that east-west line. But that sharp boundary actually coincides with where there's a line of gravity stations. So is that real, or is that artifact of the processing? Those are the sorts of things that we don't know, but I know that NTGS are very aware of this, and they're planning right now a new gravity survey to take place. So all the gravity data in this area is going to be refreshed within the next year. And that's thanks to work by people like Tanya Doon and Peter Eagleton. Here's Landsat, radiometrics, and the magnetics, which have been very, very useful. And you can see again, the radiometrics do pick out the granitic features bodies in the area. There's a body there. This isn't actually the best way of displaying the magnetics. It's just an image I've culled from one of our reports. But you can also see that it's picking out mildly magnetic stratigraphy in the area, and the fold patterns that are present. So really, I mean, the geology here is just spectacular. And the final thing to note in the magnetic data is it highlights the metamorphic aureoles around the granites. There's a relationship between those and also the Zamu dolerites, which appear to be magnetized near the granites. That's the implications from field workers who've mapped in the area. And one nice thing is coming from southeast to northwest. This is what's known as the Pine Creek shear zone coming through here, and you can actually see that this aureole, some of the material in this aureole appears to be entrained and dragged out along that shear zone. So there is information in these data sets which can give you things like kinematics or movement directions, as well as much more detailed information on the stratigraphy. So we're using this quite heavily to reinterpret the mapping of the area. Gemma and I have now just entered into a stage of drawing sections through the domain and building the first stages of the 3D insight into the area. And there is a lot of structural data available, both from industry and from the public domain maps. And this is one of the first interpretations that that Gemma's produced. And I'll just go back a step. So this is this line here coming through the middle of the area of interest. And we've just reoriented the line. So you can see north is actually off to the top right of the image of the PowerPoint slide. And here is the cross section that Gemma's come up. Now, when you do a cross section, you have to decide what rules you're going to follow before you do that section. And in this case, we've made the assumption to obey certain governing rules, which we're fairly confident are not true. We've had to assume that the layers remain parallel and there's constant thickness. We can relax those rules and look at how thickness might be varying along the section line. But as a first step, this is always a really good place to begin. And either way, what it is showing is a really interesting geometry. And this is going to be perfect data to build the 3D model, and it's going to be perfect data to then import into something like a digital twin environment. But what I just want to point out as a side insight that's come from this is that you see that along this section line, its dominant structural geometry is synclines. So it's what I would call a syncline dominated geometry, which is pretty unusual. And you get these cuspate lobate features. Now, if you step back and look at those, these look like mega mullions, so mullion type folds. And normally mullion folding is dependent on particular rheological contrasts. And is more commonly found in fairly high-grade metamorphic rocks. So the question is this mullion folding or is it something else? And I mean, it may well be mullion folding, but there is another possibility, because this kind of geometry is also found in sedimentary basins where you've had salt escape. So we might actually be looking at the remnant artifacts of salt escape tectonics under compression. And just to give you an illustration of that, here is an example from of salt tectonics from the subalpine fold and thrust belt, where there has, in these black layers here, and these are two cross sections, and you're seeing in black Triassic evaporitic sequences that under compression, or under rifting and then under compression, escaped through these purple layers, which are actually the Jurassic overlying Jurassic sequence. And the result of that is you develop these broad, synformal, cuspate geometries with very pinched anticlinal hinges, which bears some similarities to what we're seeing here. Now, the reason why that's interesting for a start, it's going to dictate the style of model that is generated in our leapfrog modeling. And but it's also really interesting from the perspective of why the Pine Creek Orogen may be polymetallic, because it hints that there is salt in the system, or has been salt in the system. And salt, we know, is a very important constituent for generating ligands that can carry polymetallic elements, like you know, a lot of the PGEs and things like nickel, and various other metals that we are finding that are present in this part of the orogen. And it's not the sort of element. In other words, it's not your classic orogenic sulfur-based dominated hydrothermal system, if that's the case. So we don't know if that's true. This is a very early stage observation, just based purely on geometry. But these are the sorts of the observations that emerge from work like this, which then lead to other questions that you can follow up in the field, you can follow up with sampling, and then you can follow up by developing new exploration models. So we're just coming to an end of the talk now, and there's just an illustration of the existing 3D model that was actually originally generated by Rick Valenta. This is the model that Rick, Gemma, and I are updating. In this case, there's two models sort of superimposing one another. There's a basement, no basement model, and then there's some very simplified stratigraphy that has been modeled in Leapfrog. And these are the kinds of features that are going to be improved upon and then hopefully pushed out as a product to the exploration industry by the end of the financial year. So to summarize, Pine Creek Orogen, data-rich domain. It's got underappreciated polymetallic and energy transition metal opportunities, which really leads to a question of whether there's potential to think about the role of salt in the mineral system here and what that means for new discovery insights. And for relative to the main point of this talk, the Pine Creek Orogen really is kind of an ideal domain to trial digital twin approaches to consuming and visualizing the data and then serving them up and making them available to the public. And more broadly, in terms of the digital twin innovations that I've shown you, we have been able to develop what we call a seamless multi-scale twin, which can be used for data discovery, and not only for that, but also for what I would call high responsibility decision making around ESG. So the fact that we can now compare ESG data sets very comfortably, very easily alongside the geoscience data sets hopefully means that we can do a much better job at decision making and permitting and landowner engagement and all that. Pine Creek itself has a lot of potential for exploration, as I've already mentioned, and this could be a really useful area to trial the twin technology. So that's it. Thank you very much.